So we ended last time with the idea of putting ions into solution, and we had generated the initial ideas of hydrophilic. Now we're going to push that a little bit farther today, and what we'll try to do is we're going to lay down a sodium chloride crystal in a column of water and ask then how the dipole moments on the water molecules will allow the ions which are locked in a crystal structure of the sodium chloride to go into solution. We're going to ask the question of how thermal energy then will randomize the distribution of those positively charged sodium ions, the cations, and the negatively charged anions, the chloride ions. So we'll go from this idea of a crystalline structure to the ions distributed in the water column, and we'll think then in terms of the diffusion of these ions in the water column providing a new equilibrium. And we'll talk about how this equilibrium is reached simply by the random walk of these molecules. Then we'll take this idea and loop back through it again and talk about the idea of diffusion of ions across a barrier. And in our thought experiment, we're going to generate a barrier between two volumes. One volume will contain pure water. The other volume will contain a sodium and chloride solution. And the barrier will not be an impervious barrier, not once we get done with it at least. It will in fact have ion selective channels so that the ions, if you think about them as ping pong balls, will be bouncing against the wall, be bouncing against the barrier. Now and again, on a random event, they'll reach just the right hole and bounce through to the other side. So from that, we'll begin to think about not just diffusion in a water column, but diffusion of ions through ion selective channels across the barrier. But again, we're going to reach an equilibrium. And now we're going to reach an equilibrium between the two columns of water, the left and right-hand sides. We'll see this over and over again when we talk about cells, reaching equilibrium and much of the energy of cells being dedicated to maintain a disequilibrium and use that disequilibrium for any number of processes. But for here, we're just going to think about the idea of reaching a new equilibrium between the two compartments. This idea will emphasize the movement of ions. But you can turn this idea on its head. You can change it round. And now in the barrier, rather than using ion selective channels, ion selective pathways, we're now going to place a water selective channel across the membrane. Ions can't move. There's no pathway. There's no clear pathway through which the ions can move, but there is one for water. What we'll see is the same rules apply. That is, and what I mean by the same rules applying is that water now is going to move from a region of higher concentration to a region of lower concentration, going to move down its concentration gradient. Well, when water moves down its concentration gradient, we have a special name for this in biology. It's called osmosis. But the idea is the same. It's simply the random walk of molecules, and in here we'll use the selectivity of a water channel versus an ion channel to describe osmosis. And I'll mention a little bit about trees in here because that's basically how trees move water. Everything to this point, top to bottom here on this panel, is going to be all about hydrophilic, water-loving, those things that easily go into solution in water, those things which are charged. And at that point now, we'll contrast the idea of hydrophilic with hydrophobic. And again, there's meaning in the term hydrophilic, water-loving, and hydrophobic, water-fearing. When we go to the other end of the spectrum, and we talk about those things which are truly hydrophobic, one of the hallmarks of these hydrophobic molecules is going to be that there is equal sharing of the electrons within the molecule, so that the covalent bonds in the molecule equally share the electrons. And one of the classic, extremely hydrophobic molecules is going to be lipids. Whether we're talking about solid lipids like animal fat, or whether we're talking about lipids that are liquid at room temperature, such as vegetable oils like olive oil. These are all triglycerides. And they're all, if you look at the structure, and we'll spend a little bit of time looking at the structure, but what you really need to draw out of the structure is not all of the details, but that the electrons are equally shared. Because of the equal sharing, in contrast to the ions, which have this charged particle aspect to them, that the equal sharing of these electrons is now going to make them hydrophobic and insoluble in water. So we'll walk our way through this, and we're going to generate some triglycerides. I'll show you the structure of the triglycerides. Whenever you think of a triglyceride, again, there's meaning in the word. Tri meaning three, glyceride meaning it's based on glycerol. We'll see that glycerol is a 3-carbon alcohol. Whenever you hear the term alcohol in chemistry or in biology, you think of hydroxyl group. So we'll see that there are 3 hydroxyl groups on the glycerol, and then we're going to match and mate the glycerol molecule with a fatty acid. We're going to see that the fatty acid structure is such that at one end of the molecule there's a C double bonded OH. That's called a carboxylic acid group. It's the carboxylic acid group which gives the fatty acid its acidic nature. That's why we call it an acid. And we'll see that this carboxylic acid, the C double bonded OH, can interact with the alcohol on the glycerol. And under the proper enzymatic situation, we can now move some electrons around, and we're going to generate a water molecule. And when we generate a water molecule, we're going to, through a process called dehydration synthesis, generate a water molecule and leave behind an ester bond that will link the carbon of the glycerol to the carbon of the carboxylic acid and the fatty acid, and that's now going to produce this ester bond. We'll see that in a triglyceride, all 3 alcohols are converted into those ester bonds to link to fatty acids. These are truly hydrophobic molecules because they're great long chains of carbons, which can be anywhere between 14 and 24 carbons long, are all sharing electrons equally. Because of that, they're uncharged. Because of that, they don't go into solution. But then we're going to use the triglycerol molecule, and maybe it won't be today, it may be tomorrow, but what we'll do is we'll take the triglyceride, and we're then going to convert that. We're going to change it slightly. We're going to leave behind 2 fatty acids. We're going to leave behind 2 fatty acids, but one of the fatty acids is going to be replaced by something known as a phosphate head group. And we'll talk about the chemistry of this. The long and the short of it is the 2 long-chain fatty acids are hydrophobic, but the phosphate head group, because it's charged, is hydrophilic. And now you have characteristics within one molecule, some of which are hydrophilic and some of which are hydrophobic. That gets a new name. This new name is amphipathic. Amphi meaning both, pathic meaning feeling. So these are molecules that have both a feeling for water and a feeling for a hydrophobic region. They can live in both worlds. And we'll find that these are a fundamental piece of generating phospholipid bilayers. They're a fundamental piece for making biological membranes. And we'll talk about that probably tomorrow.